Hello and thank you for watching my video. This is part 2 of number theory from the multiplication table. In part 1 we developed these relations involving the integer part of a fraction, the fractional part of a fraction when there's a residue, the harmonic number, and the tau function. And ultimately proved this identity, that the sum from x equals 1 to n of the floor of n over x is equal to the sum over the same x equals 1 to n of tau of x, the number of divisors function. The glare here is unfortunate, but everything you see comes directly from the previous video. So in this video we're going to let n equal 7 and get to where we were before, and then take a closer look at the curve x times y equals n. When we fill up the multiplication table to n equals 7, well, 7 is a prime, and just like any prime, there is not going to be any way to express it in factors other than 1 times 7 or 7 times 1. So they only appear in the first, primes only appear in the first row or in the first column. So other than being extended on the ends, our step curve over top of the numbers that are no greater than 7 is going to be identical to that interior of the step curve that we had over n equals 6 in the last video. So we're just adding 2 to what we had before. Our sum was 14, so obviously we're going to have 16 for this one. Let's list out the ratio, or which is the rational height of each column, and underneath we'll put down the fractional part of the division. But notice that each fractional part is just n mod x over x. In this case, 7 mod 2 is 1, 7 mod 3 is 1, 7 mod 4 is 3, and 7 mod 5 is 2, 7 mod 6 is 1, and of course it's going to be 0 for 1 and 7. So, and then the denominators are just 1, 2, 3, 4, 5, 6, 7. And as we've seen, when you list out the fractional parts like this for any number, not just a prime, the number of zeros is going to be equal to the tau function of that n, which for any prime equals 2. But look what that also proves. For any x in between 1 and n, when n is a prime, we must have a positive non-zero fractional part. So immediately we get a sense that the sum of the fractional parts when n is a prime is going to be somehow maximal compared to composites with lots of zeros, for which the more factors they have, the more highly composite they are, the smoother they are, the more that we are going to anticipate seeing the sum of the fractional parts hovering over some minimum, which maybe we can get a grip on. Expressing the fractional parts using the mod function, n mod x over x for the fraction, rather than the curly brackets for the fractional part, is nice. It's more number theoretic-y. And here on the screen right now I am showing a compact mod notations. Rather than say mod x, we let the two lines enclosing the x say mod, and then x is the modulus in the middle where it belongs. So 7 mod x over x, that's what that shorthand notation says right there. So we can rewrite that expression we had before as follows. So now we're talking and thinking in terms of residues over x rather than fractional parts. And so the x can sort of be its own independent variable, and we just talk about residues, no more fractional parts. And this does some things for us that are quite interesting, which I will be covering in a video not including this one. For now, let's add our residue ratios to the graph, draw them on the graph, and draw in our x times y equals n curve and take a closer look at that. Before moving on, though, just take a look at that expression we have there that we've developed. It's nice. It's very number theoretic-y. Let's go ahead and add our shaded areas, and we know we're at 1/2,
1/3, 3/4, 2/5, and 1/6.
Okay, so shade in our fractional areas, and then draw in our purple step curve that is on top of or above the blue curve, but still each column is a unit width of area. So the whole area under the purple curve corresponds to the n times hn term, and of course the sum of residues on the left hand side of that equation is just the fractional parts. We can make little pictographs to visualize what each chunk of this equation here is representing. Now let's draw in our x times y equals n equals 7 in this case. Let's draw that nice smooth curve. Once you have a corner point in every column, it's pretty easy to eyeball and draw relatively smooth looking. Dividing both sides by x, we get our step function y equals n over x, and of course we can factor out the n and look at it as n times the term 1 over x, and then we can integrate both sides, and we end up seeing that y is the area under the curve is equal to n log n times the log of n. But that doesn't include the first column, because the log, the area starts at 1. So if we add that first column, then we have the full blue base area here, which is n plus n times log n. Okay, so we can draw a little icon to represent the full area of each of these three curves, starting with the greatest one, the one with the greatest area, which is this n log n here. And then next we're going to have our purple function n times nh, followed by our original step function of the sum of the tau function. So that gives us three areas in descending order. We'll call A log A of h, and then we'll call the bottom one A of tau, formerly our an, but that helps key in which formula each area belongs to. And then we can express the difference of areas, like the purple segment or just the residues, using, like, if we were going to say n times hn, we could write it out as A of tau, the base area, plus the difference of nhn minus a tau would be the purple area, and do expressions like this. So let's look at the white area above the residues. What do we got? Okay, so again, thinking in terms of the entire area under each of these curves, we have n plus n times log of n. Don't worry that I don't have the factor of n in front of log n there. I'll come back around and correct that in a second. From this area, n plus n times log n, then we want to subtract the area n times hn, which is the area under the step curve of y equals n over x, with all rational numbers intact. So the area we want to compute, that the white area, as I called it before, kind of looks like 1/4 of a circular saw blade. It's going to be the difference of the formulas above these two for which we can then factor out the n, and there we have it. Because h of hn minus log n is gamma, we end up with this area, the white area, equals n times 1 minus gamma, where gamma is, of course, the Euler-Mascheroni constant. This may look slightly confusing at first because the nth harmonic number minus log of n is the Euler-Mascheroni constant. But here it looks like what we're saying is that almost sort of like the log portion is greater than the harmonic portion. But that's not the case. It's only because of that first column is included with n times hn. Normally, you would think of the steps being offset by 1 and having that one little unit area hanging over the end. So it's just a little quirk of how the gamma function is defined. And we can see that if we scale these areas down by dividing by n, that then we are dealing with the standard log function. But there are an infinite number of ways to skin this cat. So we have some choices to make. Let's check it out and see what I'm talking about. Alright, so we start with what we have so far. And if we take x times y equals n, and then we divide just the y portion by n, then this has the effect of flattening and bringing scaling down all of the y components of this, and leaving the x component or the x range intact. And so we get this flattened version of this curve, which is exactly the curve for that 1 unit area plus log of n. We could just as easily divide the x component by n and get the curve of the log function as if we had swapped the x and y components. So it's just the same thing on the other axis. But wait a minute, we can divide any portion of n into x and into y however we see fit, willy-nilly, whatever we want to do. So we could look at y over a times x over b equals 1. Or x over a and y over b, as I've written here, where a times b equals n. And of particular interest is going to be when a equals b, aka a equals b equals radical n. Then our two terms are the same in terms of how they're scaled, and so our symmetry is preserved. But at the same time, our area under this curve remains 1 plus log of n. It doesn't matter how you assign a and b, the area under the curve will still be 1 plus log n, no matter how a and b are apportioned. So we could start with our standard representation, then take a positive a that is less than radical n, and get something sort of in between, and then we have our a equals b equals radical n, which would be our symmetrical version, and on up we can keep going until we get to our vertical representation as if we had swapped x and y. But do note that I haven't drawn these quite right because as a increases, the x range, the x width, should be decreasing as well, so it gets as thin as it is in the final one with the vertical log. Now this video is getting a little long, so let me end with a slick demonstration of this principle. I'm having a little trouble getting the mouse to properly track in the screen capture, so I can't use it as a pointer as I wanted to. Not very well anyway. But essentially this is that same graph on our multiplication table up to 12 for n equals 12. And I've got a slider for this parameter u, which goes from 0 to 1. The purple graph will stay fixed. including the light purple first column there. So the total area under the purple curve is n plus n times log n equals 12 in this case. The big whitish square is an radical n by radical n square, so has an area of n. And the unit square at the origin is colored green. And to the right of that, completely contained within the unit height of the first row, is the standard log function. I should say it's a graph of y equals 1 over x, which has area log n. And that includes that red strip on the bottom, which is the height of the 1 over x curve at x equals 12. So that red strip is 1/12 high. So let's see what happens when we change the parameter u. Notice that the upper right corner of the changing bluish rectangle is always on the x times y equals 12 curve. So the area of that blue rectangle is always 12 or always equal to n. And of course, when we get to the middle, it's going to be that same square, radical n times radical n. Similarly, we can observe as this thing tracks around that the upper right corner of the unit area down in the lower left corner, the curve tracks along that corner because that's the x times y equals 1 curve, regardless of how a and b are proportioned relative to x and y. And if we take u down to 0, then we get our vertical version of the log graph. And as we've seen, regardless of what value of u we use, the area of the curve within the blue triangle, including the red strips, is always going to be equal to 1 plus log n. Here's an example for n equals 9. You can see it a little better. And you can see that upper right whitish corner of that triangle is at 3, x equals 3, y equals 3. And when u equals 5, then the red areas are identical. And I'll end this part 2 with this one here for n equals 37, just for a little perspective. It does get very hard to see once the numbers get bigger. So that's it. In the next part, I got some more good stuff coming up. Meanwhile, please like and subscribe, and please click on the PayPal link and contribute to support my research and the production of these videos. Thank you very much, and God bless you.